All right, hello, welcome back. We've made it to the end of the first part of the second problem set, which is going to be the bonus question, which asks us to derive a closed form solution for the eigenvalues of A. So the first thing we need to do is remember what is A. A is row 1, row 2, 1, 0. Okay. I just made a big jump. I skipped. Why did I do this? Because it's going to save us a little bit of handwriting. And we're going to remember that row 1 is equal to A plus B, and that row 2 is equal to minus B. You may write AB minus B here, as you like. I just want to do less handwriting. Now we need to recall the definition of an eigenvalue. An eigenvector and an eigenvalue. There exists a vector x, and this is not the state vector. This is a new x. There's no t. Such that when you left multiply the matrix A to x, it will not transform it to some new place in coordinate space. Instead, it will remain x, but scaled. It will only stretch x by some factor lambda. And we want to know what is lambda and what is x. So we need to solve this equation. We bring everything to the left. We'll have ax minus lambda x equals 0. Now, lambda is a scalar. This is one number. This is scalar. This maybe is confusing because we might find that lambda has two solutions, and we talk about there are two eigenvalues, but there are two solutions to this equation. Lambda itself is still only one number, and you can plug in one solution, you can plug in the other solution. It's not a vector. It's not a vector, okay. X is a vector. X is a vector. We said that, and we know that A is a matrix. I'm not going to even write it. So, but to make things clear, you know that the identity matrix is defined such that I of A equals A, right? It doesn't do anything. It's like it's 1. Okay, so we can write this equation as ax minus lambda I x, okay? Because ix equals x. Now, when we can factor x out, so we'll get a minus lambda I x equals 0. And we need to know, when does this equation equal 0? So there are two situations. Situation 1 is this equals 0 if x equals 0. Okay, fine. This is dull. We don't care. And then 2, this equals 0 if the determinant of a minus lambda I equals 0. Why? That's the definition of a determinant. If you have a matrix that has a determinant 0, if you multiply any vector by that matrix, the result will be the 0 vector. Just linear algebra definition. I give it to you as a gift. You are so very welcome. So we need to solve the determinant of a minus lambda I. First, we need to know what is a minus lambda I. So let's do it. We're going to have a. So let's say what is a minus lambda I lambda, as you like. Make some delineation here. Let's change colors again. A is row 1, row 2, 1, 0. Lambda I is the identity matrix is just 1s on the diagonal times lambda. So we can factor the lambda into the matrix. Matrix scalar multiplication, you just multiply everybody. So here we have a lambda, and here we have a lambda. And then matrix subtraction, we can just subtract element-wise. So this will be a single 2 by 2 of row 1 minus lambda. This minus this is row 2. This minus this is just 1, and this minus this is minus lambda. Okay. And we seek the determinant of this matrix. Now you need to just pull out of your brain that the determinant of a 2 by 2 matrix is this diagonal multiplied minus this diagonal multiplied. Yeah, so you take this times this minus this times this. Okay, so that's going to equal this times this. Well, let's just go through it step by step. So it's rho 1 minus lambda times minus lambda minus rho 2 times 1. Yeah. So let's factor this out. We're going to get minus lambda times lambda is lambda squared. Minus lambda times rho 1 is minus rho 1 lambda. And then we have minus rho 2, 1. So rho 2. Okay, great. And this is the determinant. So now we seek, remember, we seek this to be 0. And you should see that we have a quadratic equation. Quadratic, D-R-A-T-I-C, equation in lambda. Okay. I really hope, is this running off the screen? No, it's not. Oh, that's wonderful. Okay. So we need to use the quadratic formula. So the variable now is lambda. So we have A equals 1. We have B equals minus rho and rho 1. And we have C equals minus rho 2. And we need to use the formula, which is, what is it? A plus or minus the square root of B squared minus 4AC all over 2A. Yeah. I think this is a B here, right? It's B plus or minus the square root. My song failed me. It's B plus or minus the square root of B squared minus 4AC over 2A. Okay. Okay, and so now we plug this in. We're going to get B is minus rho 1 plus or minus the square root of B squared is going to be rho 1 squared minus 4AC is plus 4 rho 2 all over 2. Done. Okay, so this is your answer. These are the eigenvalues for the matrix A. There are two. You see there are two solutions, one for the plus branch and one for the minus branch. And furthermore, we can talk about stability. So we can go even like double bonus stability. Okay, first, it's very easy to see when is this imaginary. When imaginary? Well, it's imaginary if the value under the square root is less than 0. So if rho 1 squared plus 4 rho 2 is less than 0. Okay, so there you go. That's our condition for imaginariness in the solution. And then when stable is a slightly more complex question because we have to do some casework. You need to ask, if everything's real, if you assume that this is real, then you just need to ask, when is this whole thing greater than 1? Or sorry, when is this whole thing between minus 1 and 1? Right? So if real, we just ask this. If it's imaginary, we have to think about the modulus, right? And remember, the modulus is like the vector, the length of this vector. If this is C and this is R, okay, this is the real numbers and this is the complex plane, and then you have some number, okay, like 1 plus 1j. Okay, this is 1 plus 1j. Then the modulus is this length, which is what? The square root of 1 squared plus 1 squared, right? So it equals the square root of 2. Yeah, because that's just Pythagorean theorem. It's this squared plus this squared square root to get this length. So we need to know, if this is imaginary, we need to figure out what is the real part and what is the imaginary part, which is more complicated. So we're not going to do it here. But just realize that in principle, that's all we're going to do. That's the whole analysis. And you could do it if you wanted to, if you were very dedicated. Okay, great. So that's everything that there is to say about this. Join me next time when we look at the Borrow-Gordon model. Thank you very much. Hey, it's Jesse from the future. I realized that my quadratic formula is wrong because it's minus b. It's minus b here. Okay, and then this is plus. But our analysis down here doesn't change. Okay, and because the part on the inside is right. And yeah, the only analysis that would change would be if we had gone through all of the stuff that I said we're not going to go through. Okay, so sorry about that. I hope you weren't cringing too hard as we're going through the last 45 seconds of that, if indeed you watched it. Thank you.